So welcome to this Monsoon Cafe. Today I'm going to talk about a little bit off topic. Generally, we focus mostly on the Indian monsoons. However, since I'm working on the international teleconnection between Indian monsoons and the West African monsoons, so I will give a brief overview of the onset process over the West African monsoons. And it is kind of governed by inertial instability, and it is remotely forced by the Indian monsoon onset. Okay, so before going to the exact phenomena, I would like to give a brief overview of what exactly inertial instability is. So this picture is it's a schematic picture, but in context of the boreal summer, where there is a low pressure over the northern hemisphere and a high pressure over the southern hemisphere. This kind of inertial instability comes into picture when the absolute zero vorticity contour it doesn't exactly sits over the equator. However, it is shifted northwards. So it creates a region of instability which is marked by this from equator to the eta zero line. And this instability is called the inertial instability. And now to explain it, so since there is a large scale pressure gradient, so let's say there is a parcel over this part, and so it will experience one pressure gradient force towards the northern hemisphere and some Coriolis force towards the equator. So you can see since there is an imbalance between the two forces, there is a residual force which is kind of shifting it towards the north hemisphere. And as the parcel moves ahead in time, this residual force kind of comes down. And at the eta equals to zero line, the pressure force and the Coriolis force exactly cancel out each other. However, due to inertia, this parcel still keeps on moving beyond the eta zero lines, and as it keeps moving beyond the eta zero line, now the residual force acts in a opposite to the motion of the parcel, which kind of decelerates the parcel over this part. So you can think of it in a way that the parcel is kind of accelerating over this region and it is decelerating over this region. So which in a way it creates a doublet pattern across the eta zero line, which is the convergence pattern over here due to the deceleration, and the divergence pattern due to the acceleration of the residual force over here. So this is a brief overview of what inertial instability is. Now, if you have to put this into the maths of it, then this is the equation which gives the exact meridional component of meridional acceleration of the parcel. And if you want to have a much more better look into the this how this derivation came into picture, you can look into this famous paper by Thomas and Webster. I think it dates back to 1997, where they talk about not only about inertial instability, it overall talks about the equatorial convection from the lens of vorticity dynamics. Now, if you look into this equation, there are total of three terms. One is the F term, then one is the F minus the meridional gradient of zonal means, and the delta Y term, which basically is the perturbation term. So in the subsequent lectures or in the subsequent papers which I will be discussing, people have defined this F minus BU d by dy term as the inertial instability index. So based on the sign of this index, you can think of it like if this I is positive, so this term is positive, over there is a negative here. And so if you give a positive perturbation to the air parcel, then overall there will be a negative acceleration that is being generated, which will kind of slow it down. So it's an inertially stable case. However, if this I is negative itself, then over there is a negative and negative there is a positive. So any positive perturbation or delta y term will lead to a positive acceleration of the meridional velocity. So which in turn it's termed as the inertially unstable case. So now this is a brief overview of inertial instability. Now coming on to the exact phenomena that I will be discussing in this talk is the propagation of ITCZ over the West Africa. So just like over India, we have the strong monsoons. There is also a strong monsoon over the West African part. And just like we get a ITCZ propagation, smooth ITCZ propagation over India, we don't get a smooth ITCZ propagation over West Africa. And now, if I have to discuss about temporal evolution of the seasonal cycle of the monsoon of West Africa as a whole, it starts from the month of May and it goes all the way up to September. And you can guess it of its early onset because it is much more closer to the equator. However, in India, it's much more beyond the equator, so there is a mismatch between seasonal cycle. However, this seasonal propagation is not as smooth as we would have expected. So the overall temporally the African monsoons compose of two parts. One is the coastal precipitation part, which kind of sits over this. I mean, pardon me for the this font. It's a very old paper. So this is the coastal precipitation part, and this is the Sahelian precipitation part. So those are two different parts, and people have kind of defined these two states of precipitation to be two quasi-stationary state, where the ITCZ sits over this part for a long time, then it suddenly jumps and it sits over this part for a long time. So it's kind of there's a discontinuity. It's not a smooth propagation like over India, and it's not like it's kind of propagating like this. It's kind of sitting here for a long time and then suddenly it sits here for a longer time. So, so this phenomena of discontinuity, this T0 is the onset data over the Sahelian phase, and this is T minus 90 to T plus 140. This discontinuity in the ITCZ order monsoon, authors have defined it to be the ITCZ jump or the monsoon jump. You can use either of them, both explain the same thing. Now, let's see the adjacent regions. Do we get any kind of a jump over, let's say, the Eastern Atlantic or the East African regions? So those are also monsoon regions. I mean, they also get a high rainfall. So this is TRMM dataset, and it is 9 days smoothed TRM dataset. I think it's the year is 2006. It's not a composite, but it is rather smoothed one of 9 days. So one thing you can see, this is the Eastern Atlantic, this is West Africa, and this is East Africa. So over Eastern Atlantic, you see a very smooth propagation of the ITCZ. And over East Africa, even though East Africa overall has a weaker monsoon, the overall cumulative rainfall, however, it does have a smoother ITCZ propagation. Only this over West Africa, you can clearly see two rain bands that is kind of disconnected, or it is discontinuity over there. So this also suggests that this discontinuity in ITCZ or this ITCZ jump is a very unique feature. It is only seen over this West African region, and it is not seen any of the adjacent longitude regions over the same latitude bands. So the natural question that comes into the mind is that, so this is the spatial jump. So the natural question that comes into mind is that either there is a sudden increase in the rainfall over Sahel, or there is a sudden decrease in the rainfall over the coastal precipitation. Either of them will project onto a discontinuity in the spatial map. So in order to look into the exact thing, which is that, like, is it Sahel's increase or it is the decrease in the coastal precipitation? So people have looked into the time series of the seasonal time series of rainfall for both this occasion. So you can see this is the Sahel's rainfall and this is the coastal precipitation. It is not actually the Sahel's rainfall that is showing a jump of ITCZ or the rainfall that is suddenly increased. Rather, it increases much more smoothly. However, the coastal precipitation, it shows a sudden drying, which spatially it kind of looks like as if there is a discontinuity and it has kind of jumped. However, the actual cause is actually the decrease in the drying of the whole coastal precipitation. Now, let's go back to the inertial instability, which I have discussed in the initial part. So, okay, this people have this in this paper they have discussed about two kind of inertial instability. One is the meridional inertial instability index, and one is the inertial instability index, which I have shown, which is in the zonal direction. So this green one represents the meridional inertial instability index. However, they have shown that it is not much of an important. Only important thing is the I, which I have shown here, which involves the gradient of zonal velocity. So, okay. So this solid red curve is the daily average, and this fluctuating part is the 6-hourly inertial instability index, which they have calculated. And second thing I would like to point out here is that both of them are equatorial Eastern Atlantic, and both of these are coastal West Africa. But however, they wanted to show it at a very high resolution. They have taken two latitudes for this. This is 2 to 4 degree, and this one is from 4 degree to 6 degree. And this latitudes are same. However, this is over the Atlantic one, and this is the coastal West Africa part. So, so one thing you can see, the negative values of inertial instability, which kind of shows availability of inertial instability, then it comes up very early in the season over this Eastern Atlantic part. However, if you go to this West African part, the negative value starts appearing much later into the season. So you can see the negative, most of high frequency of negative values comes later into the season. And also with this one, I would like to also show the importance of high resolution, temporally high resolution data. So you can see in the daily average, even though the inertial instability index shows a decreasing trend, however, except one day, I don't see much of a negative values that would be being calculated with the inertial instability index. Rather, the high resolution data shows that okay, there is a negative inertial instability index. With the day data, I don't think we can conclude that there is a negative inertial instability. And okay, so what this says is that there must be something over this region which kind of maintains this inertial stability. Again, since we always talk about instability, we always tend to think it as kind of a convective instability and convection. So I would like to point out that not all kind of instability leads to convection. This is a special type of instability which kind of the stability kind of supports convection and instability kind of inhibits convection. So the convective instability is always in the vertical direction, and this specifically it is defined in the horizontal surface. It depends. You can take the isobaric surface or the isentropic surface. However, in the paper by Thomas and Webster, they have referred to Salzburg work which dates back to 1960. They have said that if you define the initial instability in the surface of constant angular momentum, it translates into convective instability. So again, it's a perspective of where you define the instability. So in this case, they have defined it in the isobaric surface. So in coming back to here, so we get a high frequency of negative I values over this region. So basically, there should be some forcing which is kind of making the region stable and kind of letting the convection happen. This is exactly where the role of African easterly jet comes into the picture of how it helps in maintaining the stability over this region. So this is a plot which is so this one is like I think 15 or 20 days composite of again they have taken only one 2006 composite picture of the African easterly jet before the jump, and this is after the jump. So basically it's the before and after the onset of the Sahel. So again, if you were not clear with the African easterly jet, it's a geostropic jet which kind of sits in the mid-troposphere and it kind of covers the West African part. And it actually, even though in this part, due to the color leveling, it shows that it sits only over the West Africa. However, we have found out that it is kind of now expanding into the East African part also. So nevertheless, so the most important thing of this African easterly jet is the northwest and the southeast tilt which is there in this part. So due to this tilt of this African easterly jet, it maintains a strong negative meridional zonal winds gradient. I mean geostropic zonal winds gradient over this part. So it maintains this negative value. So you can say this is a negative value with this minus the overall maintains a positive I value, and it's kind of helps in maintaining the stability. And however, if you go to the Eastern Atlantic part, due to this northwest tilt of this jet, and even though there is some gradient over here, since we are moving ahead, the F starts to increasing and it starts to dominate. So overall, I mean, it doesn't make sense to define an inertial instability index here because anyways, this is a gradient. So anyways, the gradients are tend to be very small. So overall, the F starts dominating. So there is no question of inertial instability. It only comes when we define it near the equator. So you see this plot. After the jump, this African easterly kind of shifts northwards, which kind of makes this coastal West African part susceptible to negative I values, or also susceptible to inertial instability, which kind of, if you remember this convergence divergence doublet pattern, so it helps in kind of creating a divergence pattern over here, which leads to the drying up of this region. And because there is a overall divergence due to the inertial instability and kind of over the precipitation band, it looks like it sits over this northward part over the Sahelian phase. And existing literature, they say that this African jet movements, it kind of follows the solar insolation, but I haven't looked into it as of now. Now, so this is we have established what exactly drives the drying up of the coastal phase of the African precipitation. Now, the second part of my talk would be the remote forcing from the Indian monsoons. So till now, most of the literature they have focused, or like if you have to study the onset of a Sahel, they have picked up the onset data over Sahel and analyzed the whole discontinuity. However, what we have done is that instead of picking up the onset date over the Sahel, we have picked up the onset date over the core monsoon zone. So this day zero represents the onset date of the core monsoon zone. So you can see, so by the way, this the onset date of Sahel, it has a standard deviation about 8 days or so. So with that high standard deviation, I wouldn't expect such a clear picture. However, we do see a clear picture where the day zero being the onset date of the core monsoon zone, after about 10 or 15 days, on the onset itself, the coastal phases started drying. And after like 10 or 15 days, it kind of shifts northwards, which this overall clean signal also suggests that there should be some remote forcing from the Indian monsoon onsets, which kind of impacts the onset over the Sahelian phase. So it's not that people have not looked into it. So people have talked about the westward propagating modes. So generally what the known mechanism is that whenever there is this BSI propagates northwards and it reaches the core monsoon zone, it triggers a Rossby wave kind of a pattern towards the western side. And that, so this is the OLR pattern. So you can see once this convection is triggered here, it kind of moves to the west and it triggers convection over here, which kind of leads to moist convection over this West African part. So people have talked about this, like Sterner et al. Has talked at the international scales, and Yannicott et al. Has also talked about the onset part. And in our work, what we have looked into is the structure of this westward propagating modes. So here we have filtered out the geopotential, the potential vorticity at this particular filter 10 to 20 day in the zonal wave number of 1 to 6. So what we have picked up this day zero is, this is not the onset date. This is the onset of the active spell over West Africa. So we have picked up the onset of the active spell over West Africa, and we have traced back the overall geopotential low which sits over there, and seen from where exactly this pattern comes from. So you can clearly see that there is a westward propagating overflow wave that is seen here, which kind of in, let's say, day minus 12, it sits over this Arabian Sea region and it kind of propagates westwards. And if you have to study the vertical structure of this, so this is the vertical potential vorticity structure, and you can see there is a strong potential vorticity core over this part. This also highlights the importance of the African easterly jet, which also sits over this part. So our we have looked into this particular wave and African easterly jet interaction, and shown that it helps in propagation of these waves to the West Africa. That is how the overall teleconnection comes into picture. However, till now, one thing is not clear is that whether these waves helps in the northward shift of the African easterly jet, which I have shown here. Because again, this is a very clumsy picture, I would say, because they have defined the inertial instability index based on the hourly data. However, showing the African instability, that they have taken a composite of like 10, 20 days. So it wouldn't kind of directly reflect the exact causality, whether this shift is due to the waves or the instability is triggering this shift. So it doesn't mix, like the causal pattern doesn't comes out here. But however, they have shown an overall diagnostic mechanism of how the inertial instability sets up here, and kind of the drying starts. So yeah, the next what we are looking on is that how these waves create moist convection over this West Africa, and also whether the shift of the African easterly jet towards the north is due to these waves, or is it due to something else? Because people have talked about the northward shifting of the solar insolation, and also they've talked about the Saharan heat low, which also has an impact on the shifting of this jet. And so yeah, it's still a work in progress. So yeah, to conclude is, we have discussed about this contain the West African jump, and it has been attributed to the inertial instability over the coastal regions. And also we have shown that there is a remote forcing from the Indian monsoons, at least on the onset part, which kind of triggers the onset over this West Africa. So, yeah.
Yeah, can you exact difference between the date of the onset, the core monsoon zone, and the jump? How many days?
So what we have seen is that these waves, this active spell, it takes about 10.
I want the PDF.
Okay.
do a PDF, it was trying to see how much spread is,
Spread.
right?
Mhm.
So they're very valuable to make a point that it's pretty narrow. But what is the climatological shift in
It's about mid-July or
mid-July?
over Sahel. Even though the West African
It's
may,
almost a month after they.
yeah, it's
Yeah, that's a long time.
uh,
So if the northern are conquering, they'll go very quickly, right?
yeah, but again the cold monsoons. So the difference is about 15 to 20 days. The onset of cold monsoon zone and the onset of Sahel, like roughly we have to say if we have to look into. So even the cold monsoon zone starts like say if it starts in mid of June. So yeah, I mean like July first week or second week, then this should happen. The onset over Sahel should happen.
Whether what's happening from India is essentially conditions are atmosphere over Africa for the jump.
That's exactly what I was
We
saying.
have to look at water vapor and other things too. But it's very interesting. And what is the paper strand of it?
Yeah, that's actually machine learning based people where they have seen the synchronization of Sahel and Indian monsoon. So they've said that okay, it is synchronized. The extreme rainfall, not the droughts. They've not the breaks. They have not talked about. The active spells are kind of synchronized.
Okay. Yeah, the Indian monsoon is still going pretty good, although the predicted weakening has already occurred. And the best way to understand this is that June was 9% above normal, July was 5%. Look at August. Okay, August is minus 26, only 5 days are over, there's still time. And I want you to notice the important difference between country as a whole, Northeast India and East India. See the big difference. So plus 40% over East, plus 20% over Northwest, high minus here, and of course, high minus here. So very interesting feature, okay? So there's been a shift in the system that you saw in the prediction by ECMWF, okay? But still, of course, the cumulative is doing quite well. And you look at the time series, yeah, this has been predicted. This decline on the end of July is clearly seen, but it's not completely a breakthrough yet. Okay. If you look at the cumulative rainfall district-wide, to me it looks very interesting. Entire region where the lows travel up are all extremely high. Okay. In the coastal Himalayan foothills is below normal, and of course Maharashtra is somewhat below normal. And this is interesting. I didn't realize that this part, not coastal, but what they call Manland, it's above normal. That's a bit surprising. This is the cumulative. Okay. Now I'll show you the dramatic change between cumulative and what is happening in the last 6 days. Look at the difference. Last 6 days, everything has changed. This entire belt has become below normal. Okay, this entire belt where that so-called cloudburst occurred is here very high. Okay? Now, of course, we are starting getting very heavy rain, but coastal rain here has declined. Okay, this shows clearly a shift in the nature of the monsoon rainfall. Okay. Now, as all of you know, when it comes to the end of July, IMD makes a prediction for the next 2 months. Okay? You can look it up. Okay, they say rainfall average over the entire country, August, September will be this month, above normal. Okay, and they actually predict a number 42.8. Okay, so far. Sorry, no, this is the climatology. Take the 6%. This is what we are predicting. Okay. This is the final number. So remember this number. So the end of September, we'll look at this number. How close we have come in the middle of the monsoon. Remember, when you do it in May, there's a large error bar, no question. But by this time, this error bar should be low. I mean, anybody has checked it. It's worthwhile to look at all their predictions in the mid season and see whether the 4% error bar it should be lower, because already half monsoon is over. You know that number, and this number should be predictable much more accurately. So we'll examine that this year. Now, the interesting part about this year is IOD. Okay, El Nino is mostly neutral. We don't even worry about it. Don't talk about it. But IOD is behaving in a funny way. Why? The last few days it has plunged actually from 0 to minus something. Now, let's look at the numbers. The numbers are important. This is weekly value. Okay, all hovering over 0, 0, 0, 0. And 14th to 20th July, 0. 21st to 27, minus 0.44. And already minus 0.6. So you can see the huge transition, okay? And I'm sure there are many people who will say this present weakening of the monsoon is due to IOD, okay? I don't believe in it. I don't think it's that simple. It's convenient to associate these two, but I don't think that's simple. Now, why is that happening? Is because this part of the Indian Ocean is not very warm, more than 1 to 1.5. And something here I don't fully understand. Maybe there is a strong Somali jet in the early part. This is below normal. This is due to Somali jet, definitely. So if you look at this gradient, there's a clear aesthetic gradient here, okay? And that's what is causing IOD anomaly. But if you recall, Sulochana Gargal suggested equine thing based on wind, which is useful. And the wind anomaly here now is highly positive. Okay? 12 meters per second. Okay, it's not a minor anomaly. So the wind is blowing because of the low pressure here compared to this, because there's a much higher acidity. There's a strong zonal wind coming here, okay, and that's preventing the upwelling which is going on there. Okay? So that is the point here. So this showing up, this was not there a few days back. Okay, so I want to follow through, but also notice in association with this westerly wind anomaly, there's a strong weakening of the westerly direction. Not just here, all the way. That is there in the Eastern Pacific forecast. Remember, that forecast showed same thing is there, very clear. The question, how did it come suddenly? Okay, so you go back. This is 3rd August, 2 days back. Now you look at velocity potential. If you want to understand circulating changes on a large scale, velocity potential is the only useful metric. Okay. Now, what does it show? It shows actually a sinking motion over East Asia, West Pacific. Okay, this one, and so that is causing all this problem. We follow that. It's 3rd August. We'll see what happened. We look at 21st July, about 7 plus 10 days back. You see, it was here. Okay, this one went all the way and caused all these changes here. Now, you go back further, it starts over West Africa. I don't know whether Arindam and Ravi remember, there was some discussion during one of the courses in which Pradeep Kushwaha showed this is what happened in July 2002. Okay, unfortunately, after that, he didn't write it up and publish it. So it started from somewhere here and propagated. Okay? So this is what examining this further. So remember, there's a strong ascent motion on 20th July. It's 20th July. In 15 days, there's a movement. Okay? from below the equator to the equator. Now you look at the core monsoon zone, which is our focus always. Notice that for the first time, although having such a wonderful time in June, July, in so many days above 1 sigma, we are now having, I would add these two, 1, 2, 3, 4, 5, 6 days, almost 1 sigma or above 1 sigma. Okay. So if this continues, the potential of a long break is there. Okay. So this is really, next 1 week will tell us whether this will persist or it will swing back to normal. Now we look at the prediction made by GFS, not very good in the last 10 days. Okay here. It didn't get the observation right here. The right sign, but magnitude is wrong. Here it got too high, but finally it got the. So what I would like to remember is that any large-scale future of the kind which is able to show that GFS will get, of course. So this is the decline that you see to the large-scale reaction that is coming out connection. Now let's look at the next few days from August 1st. I would say it got this increase correct and got the decrease correct. Let's see whether it get the other part correctly. Now let's review what Asian people showed us. So last week I showed that this is slightly updated. You can see this is 20th and 4th August, that is this week really. And so this thing has come over the entire region, okay? And I want you to compare what was predicted last week, okay? I'm sorry, I skipped that thing. Yeah, okay, this 4th August to 11th August, the coming week, it is still there, it's from negative anomaly, and there is something coming from below, yes, positive anomaly. Now, this, I show you two forecasts. This is the most recent. This one is what I showed last week. Okay, slight difference is there because of changes in the condition. This is last week and this is this week. I can see that this thing is slightly weakened here. Okay? Notice that. And then we come to 11th to 18th. Then this thing shifts here. So this also has a big spatial vision. So such things, all models, but you go look up many models, they all will confirm this, no problem. Okay, this is 11th to 18th. This is a repeat, this is the old one, the previous week. And again, I want to notice slight differences are happening on a week-to-week basis. This is a little different from this. Okay, what's the difference? Sorry, this has gone back, 11 to 18, 11 to 18. You see the difference is really in this region. This part has changed, okay? The movement of that positive anomaly, okay? And then you come to 18 to 25th, near the end of August, and you can see this is target here. All the other things disappear, nothing will change. Okay? So, but there is a ring shape, but not as clear as it was earlier. Okay, next one is what was seen last week. So you can see a slight difference between last week and the present prediction. Slight difference is there. It's slightly weaker. Okay. Then we come to 25th of 1st September, according to, it still persists over Central India here. Okay. That will verify. It may not be, as you know, as you go further down, the forecast becomes poorer. This is the end of August. Okay. So it lands up in here. So let's see whether it's really true or not. And finally, they give one more week, I think they give. 1st to 8th September, it is there in, it's still there in India. Yeah, they go one more. 8 to 15. So after 15th September, forecast is given. More than a month, really. So we already saw that many models are saying September will be above normal. Okay. And which has been a trend in the last 5 years. We remember that. Okay. Now let's look at the 14-day forecast of these two models, GFS and ECMWF. They are almost identical except here. Here, GFS predicts more rainfall over foothills, okay, and ECMWF does not. This is based on last week. I did download the latest one. There's a slight difference, okay. This 5th August, I'm sorry, let me see. The 3rd August, this 5th August initial condition, and here it is somewhat weakened, okay. But I would argue that this is the key issue. GFS saying above normal, ECMWF below normal, and over Pakistan and Afghanistan, of course, they are identical. There's no difference. And over South India, they are identical. Okay. And now let's look at the forecast from IMD for the August mean. Okay. We looked at weekly August mean, and what it says is the below normal here, which is not surprising because of what's happening now, is below normal here because West Coast rainfall has been below normal. So this is a prediction. The rest of them they are saying above normal. And here you can see in view of what happened in the last few days, it may be above normal in August. Now let's compare a few weekly forecasts. This is 25th to 31st. And this is the forecast, this is the actual. And more or less I would say this is quite good. This is good, this is good. Here not so clear. And here is somewhat okay. This one was right, northeast. Okay, and that is the weekly forecast. Now, if you look at June and July, just for comparison, 2 months are over. What's interesting, both the months this region was over normal, and this was below normal. And in August, this may become over normal, and this was identical. In south, there's small difference, especially in Andhra, otherwise it was similar. Now let's look at a few short-term forecasts in view of the so-called cloud burst in Uttarakhand. Now this was a forecast for the 4th to 5th August, okay? And that's where very heavy rainfall is supposed to occur. And you can see that in the ECMWF forecast, there is a peak here, not quite where it happened, somewhere nearby. Okay? And actual value, I show you somewhat numbers, it's somewhat smoothened down in this IMD actual. The observation is a prediction. So I would say roughly it is right. Now let's come to comparison between ECMWF and NCEP. This is for 3rd to 4th August, 1 day before. And I want to notice a big difference, very relevant for extreme events. Between ECMWF and GFS, there's a huge difference in the peak rainfall. Okay. GFS is saying peak rainfall of the order of 100 millimeters per day. Okay. Right close to Uttarakhand. Well, this is not shown. This is still a problem. Predicting extreme rainfall over a small region is still very tough proposition. Models do not agree. Okay. Now let me come back to the whole discussion on cloudburst. All of you must have seen this amazing video on who took it, in which a huge wall of water, not really water, it's mud really, coming at this place and essentially knocking out all these hotels here. All the media talks about cloudburst, they don't know the basic definition. Cloudburst is when rainfall is above 100 millimeters per hour, not per day. Okay, you take it per day with 2,400 millimeters. That will never happen. Okay, but I can tell you that in my experience, this kind of thing was actually observed only in Mumbai in 2005. We have the data because Mumbai is well documented. So that was 1 millimeter per hour for a short time. Okay. Now this is not that. Now if you look carefully at the video, you will notice there are a couple of videos there. You should know all of them. Actually, this is not the main river. This is called Kirgar. It's a branch of the Bhagirathi. This is somewhere here below. Okay. So this small branch is a huge wave of mud and water coming. And in one of the videos, they showed that actually a landslide occurred on another tributary entering this one. Okay, that many people are not showing. So there was a landslide on a smaller valley on the side. Okay, and that whole thing came running down into this thing, and from there it came. Okay, so it's essentially a huge mud avalanche. Okay, this is very common during the monsoon in Uttarakhand. Okay, as a matter of fact, having gone there many times, 15 times at least, I avoided going to Uttarakhand in July and August because I have repeatedly seen every July and August there are huge avalanches, and every July and August you will see at least 1 or 2 buses falling into the river. Very common. Okay, so I always went trekking only in May and October, avoided July, August, September usually. Okay, except once I made a mistake. I went in June and I got caught. That's June 2013. Okay, now you look at the picture. This is not river. This is mud. There's so much mud came from there that this house is essentially buried in about, I would say, a couple of meters of mud. Okay? This is a mudslide. This is happening more and more often. And what's interesting is this is a serious issue of the last 10 years. The politicians don't want to talk about it because they know why it's happening. So the Supreme Court has read a very interesting Supreme Court statement worrying about Himachal, not Uttarakhand. They have said that the way you guys are building dams and constructing roads and tunnels, Himachal Pradesh will disappear. Okay, this is not my statement, Supreme Court statement. Very interesting. So clearly there is a lot of evidence that because of deforestation and road construction, landslides are increasing rapidly. Now, anybody with little knowledge of geology and basic mechanics, if there's a slope and you cut the slope for a road, entire slope is unstable. Okay, that's well known. There's no question about that. As a matter of fact, the Britishers who built the first important road in Himachal to Shimla, I don't know how many have gone there, they built the road on top, not on the bottom. Okay. Now, that's because British were running the country as a dictatorship. They didn't want to worry about human beings. They built a nice road to take them from the hot plains of India to Shimla, okay, all along the top. No problem with landslides there. But after India became democracy, people demanded roads at a lower level. Because remember, all the people live near the river bank. They don't live on the hilltop. Hilltop, there's nothing. So people, majority of villages are all on the river bank. They demanded, now they built a road along the river bank. That road is continuously hit by landslide. No choice. If the slope is like this and river is here and you build a road here, it will fall. Okay. Now, this is the peculiarity of Himalayas. Those of you who learn geology know that Himalayas are one of the youngest mountain ranges in the world. And all of these mountains, starting from Rishikesh up to Joshimath, they are not rock mountains, they are rubble. All these were, all the mountains you see, you think they are not mountains, they were the, debris that was pushed by Bhagirathi and Alakalanda over the last 1 billion years. Okay? As Himalaya rose and rivers became steeper, they just continuously dumped rubble, and on this rubble, this foothills are there, most of them. Okay, so the Shivalik is completely rubble. There is nothing to hold on to it. The only luck is that over a period of time, trees and branches grew on that and gave it some stability. Now, by deforestation and road building, we are destroying it. It's as simple as that. So there is no simple solution to this, but I think probably the Indian government was inspired by Switzerland. In Switzerland, they have built only tunnels. They have not built roads on the sides of the mountain, although Switzerland is a much older mountain than Himalayas. But the trouble is, while building the tunnel, you create more trouble. Okay, so after the tunnel is built, I think it is much safer because you're not building outside, you're building inside. because if you go deep enough, the rocks are very stable in the Himalayas also. So this is a plan that the government has. And how many people know they're building a tunnel from Rishikesh to Srinagar? Okay, that may avoid some of these landslide prone areas. But that's only for you and me, not for the locals. Locals live on the river bank. That's a challenge. Okay. Now, this place that I called Dharali. Now, I remember all these areas because I went twice to Gangotri in 1980 and 1989. And at that time, I can tell you, it was very nice. Now it's terrible. At that time, there were no cars. Cars came much later in India. There are only buses in which we travel and the military trucks, only two, nothing else. Okay? So today, there's a traffic jam there. You go there, it's ridiculous. Okay, so all these areas, Dharali was a minor village when I went in 89. Now it's a huge township, all built along the river bank, which is very dangerous. Okay, because that's where the landslide will come at the lowest point. Okay, so this is designed for disaster. Okay, here I give the actual data of the rainfall from 4th, 5th August in Uttarakhand. Okay, it's available in the IMD. Highest is this in centimeters. 300 millimeters Haridwar, 170 Nagar, Rishikesh 150. All these are not near Dharali. They are far away. Okay, they are near the border of Uttarakhand. And if you go, all these smaller values are 30, 40, 50 millimeters. So this cannot cause called a cloud burst. Okay. Now, second thing about landslide is very important. I look into it because of last year's Wayanad landslide. So landslides are not just caused by heavy rainfall one day. There's a cumulative effect. Okay. So in Wayanad, we have seen clearly that it is a rainfall in June, high rainfall followed by July rainfall, which caused a landslide. Okay. So that's a problem here. You have to look at data for the last 1 week in Dharali. Maybe it was raining not very heavily enough to encourage landslide. Okay. Now you look at the same data as the map given by IMD. All the heavy rainfall is around the Haridwar and Rishikesh area. Not here. This is where landslide occur. Okay. I've done the same thing in terms of station data. So this is somewhat smoothened. You can see all the heavy rainfall rain gauge data right along the Rishikesh Haridwar region, not here where they occur. But still, I must tell you, rainfall is a very difficult variable. It is still possible that in a small region near Dharali, there was a heavy rainfall. One can rule it out. I looked at satellite data, but satellite data is not reliable over mountains. It's okay for plains because they are using cloud top temperature as the criteria mainly. Okay, so for rain in a mountain, that may not be the only condition. Now, this is the data generated by Weibull from actual station data. Same data, he has redone it for 4th and 3rd. Okay? And you can see it is raining a lot of 3rd also. And 4th, the highest rainfall was along the Rishikesh Haridwar region, and not here. Okay? But cumulatively, it could affect it. So at that point, I might bring at the end of this monsoon cover discussion. So then I wanted to see whether I can see anything in satellite data. Now, ISRO provides a very nice rapid website. I'm sure many of you have seen it. You can look at hourly rainfall. Okay, so hourly rainfall, 4,000, not much, barely 1.52 millimeters per hour. Okay, it's not a cloudburst, definitely. Okay. Then there was a very high rainfall yesterday. Okay, after the landslide was already over. Okay, so there was a high rainfall. It's about 3 to 4 millimeters per hour for a short time. These heavy rainfall occur over a very short period. Okay, that's why it's difficult to pinpoint these. Okay, so I want to end this presentation by an interesting quote from ECMWF in their website. That what they have done is just not give access to data. Also, they tell a story about the data. I think it's a very nice statement. All of you who write papers, Remember, ultimately, your paper will be worth reading among thousands published today only to tell a nice story. So you have to learn how to tell a story. This is something people forget, that writing a paper demands as much skill as writing a novel. You have to pose an interesting question, a mystery to be solved, and in the paper you have to solve it. Okay. So this is a point, very nice point you have made. And the visual narrative. Your graphs have to be elegant. Because I can tell you today, everybody is demanding a graphical abstract. Why? Because nobody has time to read a paper. We are all drowned with papers. Okay. So first thing I look at is the figure, see whether it's, so please spend time to make your figure very attractive. Okay. So that it is, it does it. For example, the talk Bordoloi gave just now, I would like to see him plot a time series of the onset of the Indian monsoon and onset of the jet, onset of that ITCZ change in the same figure showing a clear shift. That's what will draw attention. Okay? So you have to know how to write a paper so that it attracts attention. To give an example, I'll show you one plot from one of the papers published. This is the station in Western Ghats. Okay, this is the temperature, this is the rainfall. This is the kind of graphics one has to use to show people why land sea contracts is not affecting rainfall. Because as rainfall occurs, temperature drops by 5 degrees. Okay? So nice graph to show that the rainfall causes temperature change and not vice versa. Okay? So this is what I would like to point out. Very important in today's world when you have good graphics package in which you can do well, but you have to spend some time. So many people think I've done a lot of good work and I'll put it in tables. And no, you have to do it in a nice looking graph in which you convince the reader about the idea you are projecting. So once you have to be clear about what is that you are trying to tell, what story you tell, and that story has come out in graphical form. Okay, thank you. So next week it will be Chetan Kumar Jalihal from IIT Hyderabad. I'm sure you have the interesting story to tell. Thank you.